JPL. We've got representatives from the InSight, Juno, and Dawn missions, and I will just quickly introduce them, and then they will come up and give a brief overview, and then we will sit down and have a bit of a discussion. Bruce Banerdt is the principal investigator for NASA's InSight mission and a planetary geophysicist with a career-long interest in the processes that change the surfaces and interiors of planets. Bruce has been working for many years to put a seismometer on Mars in order to bring the power of Earth-based seismology to the red planet. Suzanne Smrekar is the deputy principal investigator for InSight and for InSight's Heat Flow and Physical Properties Package, or HP3 instrument. Her research focuses on the thermal evolution of planets. InSight will give her a chance to gather key information about a missing piece of the evolutionary puzzle. Steve Levin is the project scientist for the Juno mission, which launched in 2011 and will arrive at Jupiter in 2016. An astrophysicist, he's also the lead scientist for the Goldstone Apple Valley Radio Telescope project, in which students learn by doing real science with one of NASA's radio telescopes. And all of our sites should have brochures for the Gabbert project. Tim Weise is the Dawn Deputy Mission Manager, and he leads Dawn's spacecraft engineering team, which operates the Dawn spacecraft throughout the mission, from launch, through cruise, through asteroid operations. Doesn't that sound cool? Asteroid operations. And Sami Asmar is the supervisor of the Radio Science Systems Group for the Dawn mission and the lead scientist for the radio science for the Deep Space Network Science Office. His skills include coordinating gravity field analyses, planetary interior modeling, ionospheric detection and structure, and development of the radio science instrument. So we're going to get an overview of those three missions from all five of our panelists, and then we'll sit down and have a bit of a panel discussion on topics kind of common to all the missions.
So good afternoon. Wow, a mission overview in 5 or 7 minutes. That's going to be a little bit tough, but I'll go as fast as I can. So we have there's the first slide. So this is InSight. It's sort of the latest mission to Mars. It's going to be launching in a few years. It's a lander. As you can see, it looks a lot like Phoenix, and that's not actually an accident. So there's sort of three things about a mission you need to know. You need to know what it wants to find out, how it's going to find it out, and sort of how it goes about doing that business. So the first thing, what we want to find out, we're really looking at trying to figure out sort of the basic building blocks of the way planets are put together, and specifically rocky planets. You can't really read this because it's not in focus, but if you could read it, it would say that the goal, I could read this one. The goal is to understand the formation and evolution of terrestrial planets, and terrestrial planets are planets that are made mostly out of rock as opposed to the gas giants or the ice giants. There, now maybe you can see it. Still a little bit fine print. And the reason why we would like to do this is, first of all, we're curious, of course, but also the way that the planets are put together has a fundamental bearing on 4 billion years later whether you can live on that planet or not. So the way planets are put together at the very beginning sort of sets the stage for habitability, and we want to understand how habitability either comes to occur on a planet or not to occur on a planet. Both in our solar system, we have a pretty good idea of what's habitable and what's not, but now we're getting information on exoplanets and such, and the limited information we can get on exoplanets, we'd like to be able to sort of put that together with what we know in more detail about the solar system that we live in so that we can understand what's going on in the wider universe. Okay, so terrestrial planet interiors, turns out there's a lot of similarities, and that's why we can go to Mars to learn about something about the Earth. So all these planets have the same general structure. They have a very dense metallic core. Sometimes it's molten, sometimes it's not molten, depending on the temperatures and pressures. Outside that core, there's a mantle of rock, and these rocks are not necessarily the kinds of rocks that you pick up in your backyard. These are denser rocks. The atoms are squished closer together because it's under high pressure, and they make up the bulk of the planet, anywhere from 75 to 80% of the planet. and that's what we call the mantle. And then finally on the outside, we have a crust, which is made up of less dense rocks. These are the rocks that you trip over when you go hiking. This is what we live on. So the crust is what we actually experience on a planet. But it's actually a very tiny fraction of the actual planet. But we would like to know what the sort of the interior geography is. How big is this core? What's its density? What's it made out of? How dense is the mantle? That tells us sort of what the elemental composition of it is and how it evolved. And finally, what the thickness of this crust is, which is kind of the little scum that floats on the top. And by knowing those sort of basic parameters, we can actually put very strong constraints on our mathematical and physical models of how these planets formed. And that gets into a lot more complication than I can do in 5 minutes. So I'll go on to how we're going to get there. We get there with a spacecraft that has been flown actually twice before. It's flown once in 1998, not terribly successfully, but much more successfully with Phoenix, which went to the poles of Mars. So we're actually reusing the same design as Phoenix did, which is saving us a lot of money. This is a mission that was done under the Discovery program, which is a cost cap program. So we have a cost bogey that we had to hit. That was $420 million, which is pocket change for NASA, but it's enough to get us to Mars. And so in order to get under $420 million and still land on Mars, which is a very difficult and expensive thing to do, we used a design that was already proven, already built, and we can make it a lot cheaper than we can come up with a brand new design. And so it goes to Mars all kind of buttoned up in this cruise capsule. Once it gets to Mars, it comes apart, maybe not this much. It has a parachute, comes down on rockets, and finally unfurls itself on the surface like this, and we deploy our instruments to the surface. So sort of the basic pieces of this mission, we're launching in March of 2016 from Vandenberg Air Force Base right here in California, not from Florida. This will be the first planetary launch, unless you count the moon, that ever launched from the west coast of the U.S., and that's because we're actually using a larger rocket, has a lot more energy, so we don't have to use the gravity assist of launching east over the ocean from Cape Canaveral. We take the express lane to Mars. We get there in about 6.5 months, and so we'll be arriving in September of 2016 on Elysium Planitia. Okay, so InSight is kind of funny in that when we sold this mission as having two instruments. The two instruments are the seismometer, which you can't really see here because it's covered up by a wind and thermal shield. It's on the surface, and we need to protect it from the wind and thermal variations, and so we have a dome that we put over it. And it's put on the surface by this robotic arm here, which we call the IDS. This is an old picture. But anyway, this is the IDA, the instrument deployment arm right here, puts the seismometer on the surface, and then picks up this dome and puts it over the top. Then it goes back and it deploys our second instrument, which is called HP Cubed, the Heat Flow and Physical Properties Package. This is a mold that goes down and measures the heat flow. Sue will talk more about that in a minute or so. But we actually have a lot more stuff going on. First of all, we have a radio science experiment that Sami's actually working on our mission. This is called RISE. I don't remember what the acronym is right off the top of my head, but the R is for radio, and what it does is it actually measures the position of that spacecraft in space to within less than 10 centimeters. We hope to get down to about 2 centimeter accuracy from the Earth, measuring that location on Mars. And as we measure that location as it goes around the planet, we can actually watch what the rotation axis of the planet is doing. And as it wobbles, we can actually measure that wobble, and the size and frequency of that wobble tells us about the state of the deep interior. Okay, and then we have what we call our stealth payload. This is all kinds of sensors that we have on the spacecraft that we didn't actually tell NASA that we were flying as instruments. We said they were engineering sensors, and so they kind of go in under the radar. And these are our wind sensors. We have a pressure sensor on the inside. We have a radiometer that looks at the surface, and we have a magnetometer that measures the magnetic field. And the reason why we have to do that is because this seismometer is measuring extremely small displacements on the surface. When an earthquake occurs on the other side of Mars, goes through the interior of Mars, gets affected by all the rocks as it goes through, and then vibrates as it hits the surface here, those vibrations are as small as a hydrogen atom. And so we are measuring those variations of the surface, the motions of the surface at a subatomic level. And to do that reliably, we have to get rid of all the other effects. So thermal effects, magnetic effects, pressure effects. So all these things we have to measure very well. Even if we have the seismometer well shielded, which we do, we still have to measure the effects that take the residual noise out of our signals. And so we have lots of different instruments on here, and they can be used for lots of other kinds of science. Okay, people always ask me, how do you know that there's Mars quakes? And the answer is, we don't know for sure that there's Mars quakes. We have theoretical calculations that convince me that we're going to see plenty of Mars quakes. But even if we don't see Mars quakes, which happen on faults like these, we see lots of faults on Mars. All those faults had Mars quakes on them once. We have reason to believe that they still have some on some of them. But even if we don't have faulting on Mars, we know that we're going to have meteorite impacts. This is a plot that actually shows meteorite impacts that have been seen on Mars by the Mars Reconnaissance Orbiter going over with his high-resolution camera, takes a picture of a flat plane, comes over a couple months later, and lo and behold, there's a crater there. It's found hundreds of these on the surface, and so we know that there's meteorite impacts. It wasn't actually a surprise, but it's nice to actually see it. We have the Phobos tide. Phobos goes over the surface every 7 hours or so, and as it goes over, it actually pulls up the surface a little bit, and the amount that it pulls up the surface depends on how big the squishy core is underneath. So if you have a big squishy core, you get more displacement. If you have a small core and more solid rock in between, you have a small displacement, and so that'll tell us something about the interior structure. And finally, we have atmospheric excitation. So as you have turbulence that goes over the surface, it actually pushes the ground up and down, and that creates seismic energy, and that energy will organize itself into resonances, and those resonances tell us about the thickness of the crust and some other information. And so we have lots of other things besides just seismic energy to use in order to make these kinds of measurements of the deep interior. Then we have the heat flow probe, and I'll have Sue talk to you about that. That's her specialty.
Okay, so this instrument is really taking the temperature of the planet, and it has, as Bruce mentioned, a self-penetrating mole that is going to take this tether of temperature sensors down to a depth of about 5 meters. And it does that by having a spring that moves a mass up. That mass is released, and it basically hammers itself into the ground. And we've done this many times in test chambers on Earth and scaled things to Mars, so we're confident it's going to be able to make its way under the ground on Mars. And this is something that was last done by the Apollo astronauts, close to 50 years ago. They had a drill, and they drilled a hole into the surface on the moon and deployed a heat flow probe. So this time we're doing it robotically on Mars. So we measure the interior temperature by having this tether with temperature sensors that trail behind. And as it goes down, it actually stops every 50 centimeters, and it sends out a heat pulse into the ground, this metal part at the bottom with the hammer in it. So that metal part is heated up, and a heat pulse travels out into the surrounding soil. And from that rate at which it cools down, we can tell what the thermal conductivity is. So by having temperature sensors and thermal conductivity, we can actually measure the temperature that's coming out of the planet. So, oops, wrong way. So since your workshop is about scales of discovery, I thought I would talk about the scales of temperature that we need to measure in order to understand really what the heat budget from the interior of the planet is. Our ultimate goal is to be able to understand how much radiogenic material is in the crust and how much heat is coming out of the interior of the planet through convection. Now, by making a single temperature measurement in one place, we can start to estimate that. So, but in order to do that, we have to understand all the other thermal effects at different scales. So we have to know how much is our lander on this scale of meters changing the temperature. HP3 will go down to 5 meters, but we know that the temperature from the lander will create a slight disturbance at shallower depths, so we have to take that into account when we estimated our thermal gradient at depth. And we also know that different thicknesses of crust and topography will have an effect on the temperature. So, just as on the Earth, the temperature is at a different value at different elevations, the temperature changes with elevation on Mars, and it also changes, and that has an effect basically on the temperature at the subsurface. Thicker topography can act like a blanket, more insulating topography can act like a blanket, so we have to calculate those effects as well. And then finally, we can estimate how much radiogenic material is distributed by the thickness, by having different thicknesses of crust all around the planet. Because with seismology, we'll get an estimate of the crustal thickness, and we can infer how much radiogenic material is in our site, and then estimate how it is distributed around the rest of the planet. Okay, so, and I know you're also doing an activity with craters after this part of the seminar, so I just wanted to say a few words about how we're using impact craters to select our landing site. You can imagine that a big impact crater has a steep slope and it's going to create a hazard, so we want to avoid those. But in addition, we are also using small-scale impacts, which are not particularly hazardous to us landing, as a means to understand what the subsurface is like. For the HP cubed, we want a regolith that's not too rocky. So what we have done is looked at small craters, and here's a 50 meter bar. So you can see these are pretty small craters, and what we've observed is that craters that are greater than 50 meters across excavate boulders. Those that are smaller do not excavate boulders. So that is telling us something about the subsurface. It's a probe that we use. Obviously, as an impact crater forms, it excavates stuff from depth. So those boulders are coming from depth. And basically, there's a rule of thumb that the crater excavates material from 1/10 of the diameter. So if it's a 50-meter crater, it's excavating stuff from 5 meters. So what this is telling us is that there are no rocks in our site in the upper, say, 5, 10, even 20 meters. And so basically, by looking at these small craters that excavate no rocks, we can tell it's rock-free. And we even see in one fault in that area, we can see the regolith sitting over this more rocky layer. So in one particular area, we're able to get a window into the subsurface and see that our region looks promising for the mole penetrating. Okay, I'm going to turn it over to the next mission.
All right, well, I'll continue the tradition, apparently, of talking really fast. Let's see, except that how do I get past, this is what you just saw, okay. Let's see if I can find my, here we go. It's on here, but it's not on there. Let me try that. I did, but let me try it again. There we go. Okay, so let's see. Juno is a spacecraft. It's on its way to Jupiter. We had an Earth flyby. I think you just learned a little bit about flybys not too long ago, so I'll mention that. That was October of this past year. And so we launched it in 2011. We went out without enough energy to get to Jupiter, because that would have taken a bigger rocket than we could afford. But we got out past the orbit of Mars, fired the main engine to aim, and came back and did an Earth flyby to get finally enough energy to get out to Jupiter. We're on our way now. We're further from the sun than we've ever been, and getting close to 3 AU, and it'll get out to Jupiter 4th of July, 2016, and I swear that's a coincidence that it's 4th of July. Okay. It's the first solar-powered mission to Jupiter. We have a bunch of science instruments on board, which I will tell you about shortly. What we're going to do with the spacecraft when we get there is put it into a polar orbit about Jupiter. So the basic idea is that we go into orbit about Jupiter, over the pole, come very, very close to the planet, and then spend 11 days out far from the planet, and then do it all over again, every 11 days for a year, doing these passes by Jupiter that take a couple hours pole to pole and come very close to the planet. And as you see, that's a great way to do our science. But before I tell you about why it's a great way to do our science, you should be asking yourselves why. What science are we trying to accomplish? Why are we sending a spacecraft to Jupiter? And the answer is that if you look at Jupiter, even though Jupiter is the largest planet in the solar system by far, more than twice the mass of all the other planets combined, even though it's been known as a planet since planets were known to exist at all. Even though we've been studying it for hundreds of years, even though it's one of the very first objects to be looked at with a telescope to do astronomy, and even though we've had other spacecraft in the system, and the Galileo spacecraft spent close to a decade orbiting Jupiter, there's some basic stuff we don't know about Jupiter. When you look at the giant planet, mostly what you're seeing is the tops of the clouds in Jupiter's atmosphere. We don't know how much water there is. We don't know whether there's a core down there or its atmosphere all the way to the bottom. We think there should be a dense, probably liquid, not solid, core down near the middle of Jupiter, somewhere between 3 and 20 times the mass of the Earth. We have no direct evidence yet that it's there. We don't know how it formed. We have theories about how Jupiter formed, and that's crucial to understanding how planets and the solar system form, because not only is Jupiter the largest, so that if you understand how Jupiter formed, you're understanding how most of the planets formed all by itself, but also because it's so large, we're pretty confident that it formed first, and it will have affected the formation of all the other planets, affected the formation of the solar system in general. So there's a lot we want to know about Jupiter and a lot of basic stuff we don't know. It's got a huge magnetic field. We don't understand that well how its magnetic field is generated. We think it's generated by an ocean of liquid metallic hydrogen inside the planet. So think about that for a minute. Hydrogen gas, the lightest element there is. If you filled a balloon with hydrogen here in the room, it would float up into the sky. On Jupiter, because it's so large, the gravity is so high, the pressure, temperature are so intense, that hydrogen is squeezed down to where not only does it get squeezed so much it's a liquid, not a gas, but in effect the electrons are squeezed right off the atoms. It conducts electricity, it's a metal. It's that ocean of liquid metallic hydrogen, many times the size of the Earth, swirling around, that we're pretty sure makes Jupiter's magnetic field. But exactly how that process works and how big exactly that ocean of metallic hydrogen is and what's the pattern of motion that does that, those are things we don't know. And they'll teach us about the Earth as well, about magnetic fields in general, how planetary magnetic fields work, because even though Jupiter's huge and it's far away and it's hard to get there to do those measurements, it's a great place to learn about planetary magnetic fields because there's nothing between you and the field generating region but a bunch of gas that doesn't get magnetized. If you try to do that on the Earth, you can crawl around all over the Earth and measure the magnetic field extremely precisely, but you can't learn about the dynamo as well because there's all this magnetic stuff in between you and the dynamo that make it harder to understand. Okay, so we have all these great questions we want to answer. How are we going to do them? Well, it's color-coded, so that's not too bad. The first off is measure how much water. That's crucial because the water tells you a lot about how and where the planet formed. If you're close to the sun, water's a liquid or a gas. If you're far from the sun, it's a solid, it's ice. If you get really far from the sun, then other materials get trapped in the ice in a different way than if you're, say, at 5 AU where Jupiter is. So if, as we think, Jupiter may well have migrated in after it formed, or may have formed from big chunks that collided together and stuck, but they migrated in to get to where it is, the amount of water we see compared to the other elements will tell us something about whether those pieces formed far from the sun where it's cold or closer to the sun where it's not so cold. Pretty sure they didn't form really close to the sun like here where it's a liquid. Okay, so to measure the water, what are we going to do? Well, you can see to get at those questions, we've got color-coded 3 things. We're going to do gravity science. Sami's involved with our mission. You'll find, pick a random mission and Sami's involved with it. So gravity science is done with radio receivers. Basically, the Doppler shift, the change in frequency as the spacecraft falls around Jupiter, tells us how fast it's falling. So as you go over the planet, you get information about the interior, since gravity comes from the entire planet. So the interior shape tells us about that core, tells us about what the structure looks like inside, which helps us learn about how it formed. The magnetometer measures that magnetic field I was talking about, so the swirling motions of liquid metallic hydrogen. If there's a core in the middle, that's going to change how it moves. If there's a big ocean or a smaller ocean, we're going to get different magnetic field. So we measure the magnetic field very accurately. And then a microwave radiometer that at 6 different frequencies measures the natural radial emission from Jupiter And even though that doesn't go very deep, it goes much deeper than you can see with visible light or infrared or something else like that. And that will tell us the water content, because water is one of the big absorbers in Jupiter's atmosphere to absorb those microwaves. So if we're seeing deep into the atmosphere, there's less water than if we're only seeing a shallow distance into the atmosphere. By measuring with 6 different frequencies, so they see 6 different ways into the atmosphere, 6 different depths, and by letting our spacecraft, as it goes past the planet, spin to different angles, so we get what we call limb darkening, where you look at the edge of the planet or you look straight down, you're seeing a different amount of air, different amount of Jupiter's atmosphere. We can disentangle all of that and figure out how much of that was water, which is probably the single most important number we're going to measure. Okay, so we get about the origin, right? We study the interior. You can see that's color-coded too. I mentioned gravity science and the magnetometer. Then it's got this giant atmosphere. There's all kinds of weather and things like that going on. We have instruments that can measure that. So in addition to the ones I've already mentioned, there's an infrared camera that's also an infrared spectrometer. Doesn't see very deep into the atmosphere, but we can learn a lot about what it's made out of and how it's moving around and so forth. And then we're doing this polar orbit where we go over the top of Jupiter's poles, and that's a great place to measure Jupiter's magnetosphere. It has an enormous magnetic field. There's radiation trapped in that magnetic field. There's high-energy particles. There's things streaming down. There are aurora, northern and southern lights on the poles of the planets. So we can use a whole suite of instruments that are shown here to measure that and take advantage of our orbit, which is really the key to how Juno does its business, and look at all of the things we can learn about the magnetosphere. And then you'll see something with no science goals attached, although of course we'll learn a lot from it, and that's a visible camera. So that's there primarily for outreach and education, for the general public to get to see how we use a camera, take pictures of the north and south poles of Jupiter, of course, because that hasn't been done before and we're going to fly over them, but also so that when we go through the process of choosing what we're going to observe with this camera and taking the data back and analyzing it, rather than have a team of scientists do all of that and then give you the results, our plan is to have the public involved every step of the way. So we'll have a website, we'll have a place where you can go and look at the decisions we're making and say, hey, you should do this and you should measure that and here's why. Have those public conversations. We'll choose the images, then the data will come back and we'll put basically the raw data out there for the general public to operate on and try to make pictures out of and clean up the pictures. We tried that at our Earth flyby. We took the raw data from JunoCam, put it out for the world to see, and a whole bunch of amateur photographers and astronomers took over and made some amazing pictures from it. You can find those on our website. Just made by people who did it because they loved it with very little help from the professionals. Okay, I'm probably already over my 5 minutes, huh? So what we'll do is I will let you see this movie, but I won't talk about it very much. This is what our orbit looks like if you put it in Jupiter's rotating frame. We have the advantage that because we're doing a polar orbit and Jupiter rotates fast, every 10 hours. Think about that, right? 300 times the mass of the Earth, it's rotating twice as fast. But because it does that, a small change in the timing of our orbit gives us whatever longitude we want. So we'll do all these longitude stripes where we wait for the timing to be just right to hit the pass we want so that we're making a net around the planet. So when we measure its magnetic field, we're measuring it all around the entire planet. And I know we're in a hurry, but I should at least wait for the movie to get through one quick cycle. Okay, so you can see the kind of net we make, right? That also lets us do the gravity science in a whole set of longitudes. Now let's, if it'll go on. There we go. Okay, that's what Jupiter looks like in the radio. 6 different channels, penetrate 6 different depths, looking at a whole range of angles. It's like a CAT scan to dissect the atmosphere. And that bright stuff surrounding the planet, those are high-energy electrons trapped in Jupiter's magnetic field, and they would fry the spacecraft if we flew through them. Wow. So what we do that other missions have not, because we're either braver or dumber, is we fly, instead of staying way outside those radiation belts where the spacecraft won't get fried because we're far from the radiation, what we do is, I don't know if you can see the arrow on here, come over the pole and fly under the radiation belts, because some guy who does radio astronomy and looks at the synchrotron radiation said there's a gap in there. And And actually, me and a few other people. I wasn't even the lead author on the paper, so I'll have an excuse if it's not right. But I'm pretty sure that's right. And we have good theoretical reasons as well for why there should be a gap in the radiation. So we fly in between the radiation belts and the planet, and of course we also do it very fast. It's only a couple hours, so even if the radiation were a little higher there than we expected, we don't spend much time in it. And we spend a long time far from the planet and come in and do it again. Nonetheless, radiation is the reason our mission's only going to last a year, because over the course of time, our orbit will progress and we'll eventually fly through the outer part of these radiation belts, spend too much time and lose the electronics. Okay, so I won't spend much time on that either. I know we're over, and I'll just show you the picture of the magnetosphere. You're looking at the northern aurora in Jupiter in ultraviolet light. We have an ultraviolet camera. If you can see this shows the magnetic field surrounding the planet and the fact that particles, electrons, have to be streaming down those field lines, hitting the planet to make these aurora. And we're going to fly through the region where they come by at the same time as we can take pictures of the planet to see it, so we'll finally get a really good understanding of the aurora on Jupiter. Okay. Bring it to a close, and the next person can try to struggle and keep up with the time.
While Tim is going up to pull up his presentation, I will just point out that this is a model of the Dawn spacecraft that he's going to be talking about. I believe the solar panels are 65 feet end to end. Some of the biggest solar panels out there to get it all the way out to the asteroid belt using solar power. It's a pretty amazing spacecraft.
Yep.
And he is ready.
Exactly. So thank you. The solar panels are actually the distance between home plate and a pitcher's mound on a Major League Baseball field. So kind of for scale, that's how big it is. So we have a disadvantage in this talk because we're not going to one body, but two bodies. So hopefully I won't take twice as long, but that's kind of how it works. The Dawn spacecraft has studied the second largest asteroid in the asteroid belt. It's called Vesta. We spent about a year there. And now we're on our way to the largest body in the main asteroid belt, which is a dwarf planet called Ceres, which is on the upper right corner. And about this time next year, we will be on approach to our first science orbit there. So from the scientific perspective, these two bodies, we call them asteroids. They're in the asteroid belt, but they're really protoplanets. I mean, look how big they are compared to the other asteroids that have been studied. If you see, let's see if I can get the pointer. Here's Eros. I think the Near spacecraft went to that asteroid, and then I forget how to say it. Itokawa, where the Japanese mission went to, you can't even see. It's like 1 pixel down here. So Vesta is here in the middle, and Ceres is even larger on the left-hand side there. So you can kind of see these are really protoplanets. They're kind of baby planets that have kind of halted in their formation, and so by studying them, we can figure out what the beginnings of the solar system really look like in relation to everything else. And we'll get to see some pictures later that'll show you just how the interactions with other planets like Jupiter factored in their formation. So we launched back in September of 2007. And as you learned earlier in your workshop, we got a gravity boost from Mars in February of 2009. And then we arrived at Vesta around July of 2011, and we spent about a year there in several different orbits, which I'll talk about in a minute. But our primary mission was to photograph the entire surface, as much of it as we could see, to comprise a topographic map to see how the geology looks on the surface, figure out the elemental composition of the bodies, as well as measure the gravity field, kind of try to determine if there's a differentiated core, and we did figure out that Vesta did have a differentiated core, and also look for moons around Vesta. We did not see any moons, and when we get to Ceres, we'll do the same thing. Let's see. So here's a picture of the spacecraft folded up, had to fit on top of a launch vehicle, and you can see some of the instruments. These two white columns on the top are our framing cameras, which came from Germany. And then this big white box on the side is our infrared mapping spectrometer, which came from Italy. So we did have international collaboration on this mission. And then something that's very unique about our mission is that we use ion propulsion to get from Earth to Vesta, to navigate around Vesta, and then move on to going to Ceres and navigate around Ceres. So if you've all watched Star Wars, you've heard of the thing called a TIE fighter. Well, TIE stands for Twin Ion Engine. So we kind of one-up them. We have 3 ion engines. We can only use one at a time, but yeah, we go. They're much more efficient than regular chemical rockets, but it takes a lot longer. It's 0 to 60. Right now, it's about 6 days for us to accelerate that fast. So, and it requires the large solar panels to get enough electrical power to drive the ion engines. So you can see, starting at the bottom right, we were thrusting on approach to Vesta, and we would pause periodically to stop, take a picture of Vesta to make sure it was where we expected it to be. And then as we got closer, we did a moon search, following up about the middle of the slide here. And then at quite a distance, we were captured by Vesta's gravity field. And you can see that's where the trajectory started to rotate in. And we just kind of slowly spiraled in around the body. This wasn't a big, dramatic orbit capture like the other missions typically do. And then we spent a brief period in a very high orbit, and then spiraled down to a lower orbit to get better resolution data. And so for context, Vesta is about 523 kilometers across. So if you're familiar with California, it would fit between San Francisco and Los Angeles. But if you unfold it, it's got twice the surface area of California. So we had to map that entire surface because it's a 3D object. It rotates at about 5 hours, a little over 5-hour rotation period. So we started in this very high altitude orbit to get kind of a global context to see what the body looked like, start detecting landmarks so that we could navigate, as well as start to measure the gravity field so we could navigate. And Sami will be able to talk to that in much more detail. And then we spiraled down to our next altitude. So you can kind of see the trajectory just slowly spiral down. It took us about a month and a half to go to this orbit. And this orbit was a 12-hour period. And I should say we would observe on the lit side, and then when we're on the dark side, we would stop and transmit all the data back to the ground. So that was a very hectic pace, because every day we had 2 tracks with the spacecraft getting all of the data back. We spent about a month there, and then we went to an even lower orbit, which was 210 kilometers, so that's, a little bit around 100-mile altitude, so very similar to low Earth orbit spacecraft, but this is way out in the asteroid belt. And this is where we got our highest resolution data for the imaging, as well as the gravity science that Sami will talk about in a minute. And then we came back out and did the 12-hour orbit again. At this point, the sun had shifted into the northern hemisphere, so we could image the North Pole. When we arrived, we couldn't see the North Pole because it was winter. And so the sun never illuminated the surface. So we were able to get a global map by waiting and doing this last orbit. And then we departed, same thing, where we spiraled out and then eventually got out of the gravity field, and now we're on our way to Ceres. So while we were there, we took 31,000 pictures. So we don't have time today to go through them all. But we did have this really neat video made. So here's the North Pole. And you can see that it's got many, many more craters than the southern hemisphere. And that's a result of 2 major impacts that basically caused so much debris to pop up that it resurfaced the southern hemisphere. So you see it's very much smoother than the northern hemisphere. And so it sort of reset the crater record. And so by studying how many craters exist, they can figure out the ages of when the craters were formed and what the age of the body is. And then you can see here coming into view is this big impact basin that went most of the diameter of the body. It excavated about 10% of the volume of the body. And that's what formed many of the asteroids or meteorites that hit Earth came from Vesta. And you can see there's the kind of the edge of the impact basin around the edges, and then this big mountain peak in the bottom. The base of this is about 110 miles across, so it's a really big mountain. Let's see. So then one more thing that may be of interest of in terms of how the spacecraft operates, we have reaction wheels, and you may have heard of other missions using reaction wheels and having problems with them. And so we're no different from those. We did have problems with our reaction wheels. We launched with 4 healthy wheels. We need 3 to maintain control. And since launch, we've lost 2 of those wheels. And so in order to keep our mission successful, we reprogrammed the spacecraft to not need 3 wheels. We can operate the spacecraft with 2 wheels or use our chemical jets to maneuver the spacecraft. And by thinking about really how to operate the spacecraft and how to adjust the parameters in the flight software, we're able to do a complete successful mission at Ceres even without the reaction wheels. And so that's just a real good testament to the spacecraft design and everybody working on it, being able to adjust how we were operating and still be able to get such wonderful science. So let's see. So the next part, Sami will talk about gravity science.
Yes, I am involved in many missions, all the way from the moon with Grail in our neighborhood to Cassini all the way out at Saturn. So this is my own personal scale of discovery challenge. I'm very fortunate to be on the science teams in various capacities of the 3 missions represented here, InSight, Juno, and Dawn. And if we do a workshop like this, maybe in 2-3 years from now, we'll have results from InSight and Juno. But for now, we actually have results from Dawn, at least at the first target, and later at Ceres. So at Vesta, we mapped the gravity field of the asteroid. So what does that mean? First of all, gravity of any planet is not one number, even though we learn in school usually for Earth, the little g gravity is 9.8 meters per second square. But that actually varies depending on the location where you're standing on the planet. So to get the gravity as a function of latitude and longitude, that's a gravitational field. And that's important to have because then you can get gravity features. So this is an actual map of the gravity highs and lows on a particular planet or a body, asteroid in this case. And in the case of Vesta, we deduced the interior structure of the asteroid all the way to the core. In fact, we didn't know if there was a core prior to Dawn and the gravity data. And we have concluded that our data, at least the right way of saying it, it does support a theory where there's differentiation of 3 layers, a crust and a mantle and a core, and that has been published. So if you stand on Vesta, on a red region, you would weigh more because there's more gravity pulling on you. And you can go on a diet and go on the blue regions, and you would weigh less. This gets even more interesting if you compare the gravity, which is still here in terms of the contours, with the topography, the physical highs and lows, the mountains and the valleys and the craters and the basins. And you see if on a topography high, is there a gravity high? On a topography low, is there a gravity low? And most of the time that's the case, as you would expect they would correlate. The extra mass of the mountain that you would see in the picture of the topography or altimetry should produce a gravity signal. But it gets more interesting when it doesn't. If you look at a mountain, and there it is in the topography and the images, but it's not there in the gravity. Or you go over a flat region, and there's no features, but then there's a gravity signal. And that's when you start probing below the surface. In the first example, there's a mountain but no gravity. The body has compensated subsurface such that the net gravitational effect is 0 or canceled out or a smaller number. In the case of a flat region where there's a gravity signal, that means there's a buried something, typically an impactor that buried itself or magma that had flowed there and got buried, and it has higher density than its surrounding area and produces a gravity signal. Now, you would never know just looking at a picture or altimetry. So this is how gravity probes the interior structure, typically all the way to the core, at least the cases of the solid, rocky terrestrial planets. And we'll see what we can find out at Jupiter with Juno. So I can speak about gravity for 2 hours, but they would not let me. So I'm going to stop here, and there might be questions we can address later. Thanks.
Thank you, Sami. So we're not going to have really time for panel discussion type questions, but I would like to take 2 questions from the audience at JPL. So if a couple of people have questions and you want to make your way up to the microphone, please do so. And you can ask a general question or specifically address someone.
My question's quick. You said there was the difference between Vandenberg and Florida, the launch, about gravitational assist. Is there a difference?
Yes, it's a rotational assist. As the Earth rotates, you sort of get a slingshot effect. If you go with the Earth's rotation, you're already traveling at the speed of the Earth's rotation near the equator, and that gives you a little bit of a boost, so you're going faster as you go up. If you and because of safety, we always launch over oceans, so we're not going over land where there's people. So on the East Coast, you can launch east, and Florida's pretty far south, pretty close to the equator. If you have energy to burn, which is what we have on our Atlas launcher, you can just launch. In the case of Vandenberg, we're launching south, which takes us over the ocean, and we don't get the advantage of the Earth's rotational velocity, but we have enough energy that we don't need that extra amount.
Okay, thank you.
Sure.
Hi, my name is Barbara Witt. I had 2 short questions. One is, what are reaction wheels and how do they work? And the other had to do with gravity. You said that, I don't even know the right words, but that if there is more of the liquid under the Earth's surface, that there would be more gravitational pull. Could you just talk a little bit about that?
Okay, I'll take the reaction wheel question. Basically, in order to point a spacecraft where it needs to point, you can use reaction wheels, which is basically a mass that's spinning. And if you speed it up or slow it down, the spacecraft will react by spinning the opposite direction. And so it's a very efficient way of maneuvering. You can be very precise with your maneuvering. And the alternative is to use little chemical thrusters that will push the spacecraft in the right direction that you need to point. So
have the advantage they don't break as often.
Exactly.
So the question about gravity, so when planets are forming and are still warm and relatively fluid, and if topography is then formed because the continents came together or mountain rose, they're still warm enough that they can compensate for this extra weight with a mushier subsurface, and to get the net effect of zero gravity. But if a mountain or the topography has formed after the planet or the surface has cooled, the planet then is too solid, too rigid to compensate for it. So you get a gravity signal that correlates with the presence of a mountain, and the inverse for the absence of matter in craters and valleys. I hope that helps.
Okay, why don't we go around to Montana State University and see if we have any questions there. We have time for maybe just one, but we'll see.
We have no questions, right? We have no questions. Our question was answered.
Now we'll go to the Applied Physics Lab. Any questions from the Applied Physics Lab?
Yes, I have one. My name is Christina Waterfield. How do you do? My question is, with the newest formation of the land that we have here on our own planet, are there any collaborative efforts using that kind of information and transposing them over to other calculations for the other planets?
Well, I mean, actually, most of the theories we have about the way planets work or the way planets are formed are formed by information we got from the Earth. And so the probes of the Earth, that's where we first figured out, that the Earth has a crust, has a core, and plate tectonics is a very dynamic process. We've learned about that in the last half of the last century, and understand more about the dynamics of planets, the dynamics of their interior, where you have convecting mantle. You actually have rocks which are not liquid, but still are soft enough to flow, that bring the heat up from the core let it come out at the surface and then sink back down. And all these kinds of things were really developed with the detailed observations we can do with the Earth. But the Earth is only one experiment. If we go to another planet with another set of conditions, and we can look at how that planet works, we can compare it with how the Earth works, and we can start refining these theories. Maybe it was just sort of a special effect that was happening on the Earth, and it's not really generalized. So we can go to another planet and see that if things are different, we can start refining our theories. And so that's kind of how we sort of move it forward. We can never make as good a measurement on another planet as we have on the Earth, because we're just, can't, haul all of our laboratories there and all of our sensors there, but we can make enough measurements there to then compare it back to the Earth. So the Earth's really kind of our baseline that we use to compare everything else against. So I think the answer is yes. I mean, we very much use the measurements we make of the way that things work on the Earth.
Okay, I think what I was asking, the echo is killing me. What I was asking mostly is that the newest formations that we have coming up over by Japan and China, have the calculations on how that's happening, is that affecting any of the calculations of any of these missions that you've already used certain measurements and calculations to get your information from the other planets? Has anything changed in how you do business, I guess?
So probably the planet that is potentially the most analogous to Venus, to Earth in terms of how it operates, is Venus. And so far, the only planet that we know of that has plate tectonics is Earth. And so I think the features you're talking about, mid-ocean ridges spreading, and in Japan, subduction zones forming. To date, the only planet that we know of that has those exact mechanisms is Earth. But we have it's been over 20 years since we've gone to Venus, and we have much more sensitive instruments than we did 20 years ago. And so, in fact, one of the things that we'd like to do in future missions is go back to Venus and look for features that are more analogous to those on Earth. Possibly subduction zones. There was some hint in the old data that there could have been subduction zones, which is the kind of process that drives a lot of the volcanism and the earthquakes in the area around Japan, where there's a one plate being pushed underneath the other. And there was some hint in the old data that may be happening on Venus, and so we'd like to go back and see if that could be happening there now. In addition, in terms of mid-ocean ridges where new crust is being formed, there's even some possibility that there could be features like that that were not fully observed previously on Venus. So that's the place that is probably the most active in terms of volcanism and tectonism. It's the same size as the Earth, so it has the same kind of heat budget in it, and is still much more active, we think, than the smaller rocky planets. And and also even some of the icy planets, the icy moons, have ridges where material is spreading apart, where the ice is flowing up, and the liquid oceans are flowing up like our mantle does, and causing spreading ridges on Enceladus, right? Enceladus. So there are mechanisms that are somewhat like the Earth, but as far as we know, the Earth is unique in the level of plate tectonic activity that it has. So we are trying to really understand what it is that makes Earth so unique.
Okay, great. Okay, let's move on to the Johnson Space Center and see if there is a question there.
Hey, y'all, me again. Okay, you had made a comment with Insight about there's one particular instrument that is checking to see if the soil is swelling, and then you made a comment about how one of the moons interacted with the surface. Is that kind of like a tidal effect, or did I just totally misunderstand what you said?
No, you got it just right. I mean, it is a tidal effect. I mean, and this, on the Earth, as the moon goes overhead, we have the oceans that go up by anywhere from inches to tens of feet. And what's not so obvious is that the ground actually rises and falls as the moon goes overhead as well. And it just happens so slowly, and we don't have anything to compare against, so we don't notice it. But we can measure it on our very sensitive instruments. And so that tidal bulge, as the moon goes overhead, again, the amount of that bulge depends on the stiffness of the planet, and the stiffness of the planet depends on the stiffness of the various layers as you go down. And so we can actually use that on the Earth. We can verify a lot of things about the interior of the Earth, and we're doing the same thing on Mars. And it is a tidal effect, exactly.
Okay, well, I think that's going to bring our panel to a conclusion. So thank you very much for coming out on a Saturday and great session. So now we're going to move into an activity called Crater Comparisons, and we're going to have an overview of it coming from Johnson Space Center, and I need to pull up our slides here. So I guess you guys are dismissed. Thank you.